So we are doing statistics, and we are measuring body height and body weight in a group of people. Would you say height and weight are dependent or independent?
Dependent.
Dependent.
Independent.
Some of you say they are dependent, some of you say they are independent.
Can you
Well,
make more specific the question?
No,
It's
you
both.
cannot make it more
Both.
specific. I'm asking if they are dependent or independent.
Depends.
It's both.
Depends.
Both.
Yes.
yeah.
Okay, I see there is a lot of
I disagree.
argument here and a variety of opinions. We will see today what it means, what it's all about.
For
We
weight,
can go to the materials folder and open the latest file that I've added, correlation.
for weight mass, for example, for weight mass, there is a dependence between height and weight.
Well, actually I'm glad that half of you think they are independent and half of you think they are dependent, because this way we will start with practically zero assumptions and we will see what simulation tells us. Okay. So I have put here two situations for measuring the height and the weight. The zeros are for charting purposes. Don't worry about that. And remember how we had examined independence in the dice the first time? There come. Remember how we had examined independence the first time? We were looking at where the values were falling and if they were falling in the same place or not. So let us start with collecting one. And right now, the height of this person is 161. Sorry, 173. And the weight is 72.6. If they are dependent, I would expect that when somebody appears to be taller, the weight will also be higher. So I should be seeing this in the positions of the dots. Collect one. And as we see right now, a dependency situation creates a behavior like this. Okay? When, for example, height goes to the left, weight also tends to go to the left. There might not be an exact match like it happens in real life. Your weight cannot be calculated from a formula of your height. There will be variations. Somebody will be heavier than their norm for their height. Somebody will be lighter. So these things happen. They will not fall in identical places, but the overall pattern will be that if here we have an example, for example, this person is relatively overweight. The height was here, but the weight jumped a little bit to the right. When we do this type of experiment, you need to reset frequently because otherwise you get confused with too many dots. You don't know where each dot is going. Okay. A general consensus right now is that they're independent. Now, when I collect a lot, I lose this information. Because right now I'm seeing a lot of data here, I'm seeing a lot of data here, but I don't have a way of knowing which dot of the height corresponds with which dot of the weight. So here I lose this information. Okay. How would it behave if they were independent? The first person happened to be relatively tall, at 185, 186, and very light. If it was independent. This time, both of them happen to be more or less in the same relative position. Continue. Reset, so that we are able to follow which is falling where. It looks like there might be some dependence with these two sums here. But generally, as we see, all sorts of behaviors can happen. Okay, the last one, was again somebody quite heavy for our standards, being quite short. Again, if I collect a lot of data and look at the two data sets by themselves, they might have a similar behavior. For example, both of them look to be normally distributed. The weights appear to be covering a range between 50 and 80, and the heights more or less around 106 and 190, with some outliers. Now, the next thing I want you to see is that if they are dependent, let's say they are dependent. So generally we would expect the taller the person, the heavier it would be. But what is the initial distribution of the body heights in our population? It might be that we have two populations included in there, and we might have a bimodal distribution, for example. Would this be reflected in the distribution of the weight? At this point, I'm not going to go one at a time, except for very few things. So dependent, 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 with some discrepancy, collect 100. Since they are dependent, not only will I generally tend to see that if somebody is taller, will also be heavier, but also if the original population consists of two subpopulations with two such behaviors, I would expect to see the same thing being followed by the weight also. So, if they are dependent, one of the two variables is somehow distributed. In this case, I chose a bimodal, but it could be any type of distribution. Then it's reasonable to expect that the other variable, which is also dependent, will follow a similar distribution. Okay. Whereas, if they are independent, anything could happen. What happens in this case? I'm making them independent, as you say, but now they are independent, and how do the two variables behave? Yes, and just describe them. Yeah, the height is bimodal, right? A lot of the population is around here, but there is a considerable portion behaving in this area. But weights, for example, how would you describe the weight? I actually made it a little bit skewed to the right. Okay. But it could be anything. Of course, these are all simulations. So what I tried to do in this point was to show you, first of all, what does it mean to be dependent? What does it mean to be independent? How they would be, the two variables would behave as data are coming and where they are placed in my chart. Okay. Right, let's go now to the next. Here, I'm going to create a quite different type of chart. One that you are most likely not very familiar with. Well, you're partly familiar. Okay, and unfortunately I could not fix the scales, so the scales will be changing, otherwise I was losing data because of the nature of the chart. Until now what we did was, I used two x-axis to put the data. So I am seeing the behavior of height in one chart, and I'm seeing the behavior of weight in the other chart. I have them both horizontal. They seem to be two different charts, and I'm just watching where the dots are falling. Now I'm going to do the following. I'm going to take the weight chart and flip it by 90 degrees. So when I collect one right now, I want you to see the following. Here is the height of the person at around 177.5. here is the weight of the person. So the weights now are going to be going in this dimension, whereas the heights are going to be going in this dimension. And here is the point that has these coordinates. So the point that has the height of this person corresponds here, and the weight, and basically this data point in this chart contains the information of the both variables. Because by looking at its x-coordinate, I can see what its height is, it's 177, and by looking at the vertical coordinate, I can see what the weight of that person is. And now I'm showing you 3 points for each person that was measured. Separately, I'm showing the height here. Separately, I'm showing the weight here. And finally, I am showing that person as it would be plotted in a scatter chart of 2 dimensions. Collect one more.
Why you didn't that from the beginning?
Excuse me?
Why you didn't that chart from the beginning and you do the other chart?
I wanted to use a picture that is familiar to you, the one that we used for the dice before. And it was exactly that type of chart that I had first. But when both are horizontal, independence can be seen by the fact that one dot can go here and the other dot can go here. Or this can go here and this can go here, or it could go anywhere. Now, I'm flipping one of the two axes just to go to the one we usually use as a tool. Okay, what we usually use as a tool involves only the black dots, not these. That's a chart that I had to put some more effort to make, and we usually don't need that. We just focus on the dots. Okay. So the new person measured, that's the height of the person, comes here, that's the weight of the person, comes here, and here is this point. Repeat now a few more. And sometimes the chart will be changing the scale because I did not fix it. What are we seeing? What are we seeing?
They're all grouped in one area, one specific
Yes.
area.
Because you did the distance to close.
Yeah, unfortunately, as I said, I tried for hours to fix the scale here. If I fix the scale, then these disappear. I'll try it again maybe with the other version. But I don't know if this was Alex.
The graph is linear because they're dependent. I mean, there's a straight line. As smaller the weight is, smaller the height.
Yes, exactly. Generally, what I try to show you by dependence is when a height tends to be high, when somebody tends to be tall, then the weight will also be high. So high here, they will meet in this area. Now what if it's smaller weight? Shorter, lighter, they will meet here. So generally, the trend is going to be like that. Okay. And we can verify this when we collect 100. Usually when you get a data set involving 2 columns, the height and weight, you're going to make a scatter chart of these 2 columns, examine if they are dependent. If they are dependent, you're going to see something like this. The dots are not all over the place. Let us see what would happen if they were independent. Now they're independent. Collect 1. It happened before here. Collect 2. Now, with relatively less height, the weight varied a lot. Collect 3. Collect more. Collect 10. Collect 100. And now let us go back and forth and compare the 2 black clouds, here and before. who will describe to me how these two clouds look different? If it weren't for this annoying.
When they are independent, they are more scattered. Their results are not gathered together. And on number 5, they're in a line and they are more concentrated.
Exactly. So yes.
Maybe in the second one, in number 6, there's a greater variability of outcome.
The variability of what?
Of outcome, the combination. Combination.
Yeah. Okay. Usually we define variability, until now we define variability on the 1 dimension, not on 2 dimension. But yes, of course, this is much less variable because it looks like the dots have to be in a certain area around that line. So they don't deviate very much from there. They need to be around there. Whereas when I go to the other to the situation where they are related, more or less, which area do they occupy? Think about it. I have this zone, and I have this zone. So basically, they occupy this entire rectangle. Okay? And the distribution of the height, which is here, which is normal, if you examine it, go along this direction, you will see that in the middle vertical I have more dots than I have in the sides. Yeah? This is the result of the distribution of this. Similarly, since they are dependent, no, they are independent here. This has its own distribution. This has its own distribution. Again, this appears to be normal. Along this dimension, it becomes denser, not so dense here, denser, 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 not so dense, not so dense, not so dense. The overall behavior also is a reflection of the two distributions that I have here. But generally, the big picture is that this occupies a rectangle with a peak in the middle that is delineated by these two zones. So one zone is this, and the other zone is this. And in here I have the data. This is to be distinguished from the previous picture, where yes, if I take the same rectangles, this one, yes, all the data are in this zone, all the data are in this zone, but not everywhere there. They are in a certain sub-range, which is where they are correlated. Okay? This one I included just to see again how this would behave when they are dependent, but they are not necessarily normally distributed. In that case, for example, the height will be you cannot see it well here, unfortunately, because I cannot reset the scale. But if you examine, you will realize that there is a mode here and there is a mode here. And this is reflected in the weights, where again you see a mode here and a mode here. So basically, this mode and this mode are one result, and they are forming this cluster of the data. And this mode and this mode are forming another area, and this also contains another cluster of the data. But they are dependent. Okay. And the picture remains that they are following a pattern and they're not scattered all over the place. Whereas, if I experiment with different distributions, but I keep them independent, so right now, yes?
So if they are independent, you cannot have a distribution in the result of height and weight. But if they are,
say that again. If they are
independent, they are more scattered. You cannot say that this is a distribution.
A distribution in the cloud, the black cloud.
But if you say they are dependent, you can say if it is normal or if it is bimodal.
Look,
here you
this has its own distribution. This has its own distribution. If they are dependent, whatever distribution this guy has should be followed by the distribution of this person. That's one side effect of our analysis. The major thing we want to think about is how does the black cloud look like? Okay.
It will look
If
like
the black cloud occupies the entire rectangle, okay, this entire rectangle, then it means that the black dots can be anywhere. If I see that it doesn't occupy, but it has to be around a certain area, this means now I have a behavior that somehow links these two. Okay? In this case, what I did, I made them independent and with different distributions. The cloud will be now nebulous. Okay, this is the same example as I showed you before. But here I have two modes. Here I have a peak that is a little bit shifted. Okay. And basically, again, you see that the cloud seems to occupy the entire rectangle that is defined by these two dimensions. Okay. And if there is a preference for where the data are, this is not because they are following a pattern, but because they are reflecting the distributions. I have two modes here. So this zone is a little bit more crowded, and this zone is a little bit more crowded, while the middle is not so crowded. This reflects the distribution of this, of the height. And I have a peak here, lower than the average of the data. It's a skewed distribution, and this reflects that along this dimension I get to be denser here and less dense. So the result is, in a way, the combination of the two distributions, but generally there is no other pattern. It's not like I expect them to be in a line or around the line or, okay. Okay. Now, or before I go there, let me ask you a question. Does the height affect the weight, or the weight affect the height?
If they're dependent.
Yes.
The height. I feel like
The height affects the weight. If they are dependent. Think about it. Somebody who is taller
he's more likely to
by
have more
the genes needs to have more weight. And, but on the other hand, if you keep stuffing yourself, will you get taller? You can get heavier, but can you get taller? Yeah, okay. When you're a little boy and you have to eat good food in order to build a strong skeleton, yeah.
Yes, okay, and a short person can also have, I don't know, 100 kilos, but
It
it's
can
more
have,
likely,
yes.
but it's more likely for a taller person to have 100 kilos.
That's the statistical variation. It is possible to have somebody short who is basically almost like spherical. Huh? And,
When we want to know about the kilos, the first thing that we ask is the height.
but when you want to know about the kilos,
Yeah, if you want to know about the weight.
yeah, if I hear that somebody is 90 kilograms and that's all I know, do I know this person is overweight or not? No. Okay. I will call that person overweight if I learn that it's actually this person is quite short. But generally, once we have established that there is a correlation, this is the subject of today's class, once we have established there is a correlation, we might ask, they are correlated, who affects whom? There is a general law concerning correlation. Let's say that two events, in this case height and weight, let's say they are dependent, they are related. There are three possible scenarios. Scenario number one, height determines the weight. Scenario number two, weight determines the height. Scenario number three, there is an unknown factor x who affects both height and weight in the same way. Scenario number one, height determines more or less, with some statistical variation. Scenario number two, weight determines the height. scenario number 3, a third factor controls both. And that's why they appear to be correlated. So finding correlation between two variables, and this would be reflected, I repeat again, graphically, it would be reflected in the fact that the dots are following a pattern. Detecting such a correlation does not tell us by itself whether one determines the other or the other determines the one, or if I have a higher power. So I expected to have more consensus in the class, to tell you the truth, about the dependence, the interdependence, the correlation of height and weight. But I chose something that where it's even less evident that there might be some correlation or not. So I chose income and weight. Would you think that the income and weight are related?
Yes.
How? If you eat more, you will get richer. If you are richer, you will eat more. But if you are richer, you might also be able to spend a lot of money in spa and have a lot of time.
If you have money, you have
Also, there can be an argument if you have more money, you can eat more healthy food.
So all sorts of things could happen. That's why we are here as statisticians. Right now, of course, I'm simulating everything. So here I'm creating imaginary worlds the way I want. I just want to illustrate phenomena and how they are reflected in our charts. So again, the same thing. Let us see how income and weight would be dependent. Tell me if you feel they are dependent right now. Play.
It says there.
Yeah, I say so, but I mean, you don't have to believe me. Are they dependent? And how does this dependence appear? How have I cooked this dependence?
Higher income.
They are dependent.
Yeah, higher income, lower weight.
Higher income, lower weight. Okay? So generally now, when a dot here tends to be higher, the dot here will tend to be lower. That's a gap dependence, just the other way. It's a negative correlation, as we call it. But it's still dependent because the distance from the average, in this case, will also more or less somehow determine the distance from the average, in this case, but the opposite direction, but they are dependent. Okay. So playing with collect one a few times, and in this case they both happen to be around the average. But generally, as we will see, when something goes to the right, in the top goes to the left in the bottom, and so on. Collect 100 again. When we have the distributions of the two variables independently, we cannot by themselves say anything. We can only realize in this case that weight is, income is normally distributed. These are thousands, of course, okay, the 20 means 20,000, and that the weight is also normally distributed in its own range. And again, if they were to be independent, we would be seeing the dots going all over the place without any obvious relationship. Okay. Now let us repeat the trick of the two-dimensional chart. Okay, right now I got somebody with a weight, with an income of 30-something. For the moment we cannot easily tell because the scale of the chart will be changing. Let us do it 2 or 3 times and see.
You have again height.
Huh?
You have height.
Height is blue, weight is red, and black is the points.
How's income correlated to height?
They're not correlated. The familiar cloud again.
Height is equal.
The familiar cloud again spreads all over the place. Okay. It is a little bit denser in the middle because both its distributions are normal, so they are more dense in the middle. So this produces a little bit more. But generally, as you see, again, I have this rectangle that extends among in this zone and in this zone. And within this rectangle, the dots are more or less scattered. Okay. Whereas now we can see a little bit better. Let me collect one more. When the income tends to be higher, when it goes horizontal, the income will go in one direction, the weight will go in the other direction. Now, the income goes in this direction, the weight goes down. Okay. So if we play enough, so what kind of a society have I portrayed here now? Have I cooked? What kind of a phenomenon have I cooked here in this case? What type of phenomenon in Fadini?
The more the income,
The first half was correct, but didn't finish. The more the income?
the less
The weight, yes. So we are portraying a society here where, for example, an explanation, either rewards low kilograms with a lot of income. This would be the kilograms determining the income. Or the richer the people, the more money they spend in keeping their body weight light. Or the genes are such that when a gene is very active, it makes you rich and light. Further research would be needed to determine the causality. Okay, who determines whom? Further research would be needed. But from this data, what I can say, since it goes down, is that income negatively, adversely affects weight, or weight adversely affects income. Okay? Now, I made it again dependent, but I now want you to compare some charts with each other. I'm gonna go directly to collect 100. And I want you to compare this with the previous chart. And tell me how they differ. In 13,
The height
Yes.
is scared.
It's
The
less
income
dependent.
is-
it's more scattered. It's called a scattered chart. It's more scattered. I can still see that there is a pattern. Okay? I can still see that the overall rectangle. I can still see that the overall rectangle delimited by these two zones is not completely filled, but if this is the pattern, generally the data can be more distant from what would be the norm. And even less dependent, I put them to be here. Now it is, you might actually even wonder whether they are independent or whether they are dependent. We are getting close to them not being so dependent. But they still are, because the overall rectangle is this, and generally this lower left corner and the upper right corner tend to be empty. You don't need to be in the other. Yes.
This is only because of the distribution of the variables.
No, it's not because of the distribution of the variables. It is because of how strongly they are correlated or not. Okay? So when we study whether two variables are correlated, there are more or less two things that we need to establish. One, how much are they correlated? And if they are, two, in what way are they correlated? The answer, in what way, sorry, the question in what way has two answers, positive or negative. In the first examples that we examined, here, we have a positive correlation. Linear functions, the keyword from linear functions, positive, positive slope. Okay. So positive correlation would generally correspond to a line that has a positive slope. Negative correlation would correspond to a line that has a negative slope. That's the answer to the second question. In what way are they correlated? The first question, how much correlated, basically means the one that is dependent from the other, how much freedom does it have to vary? Okay. How much freedom does it have to vary? If there is not much freedom, and it must be, let's say, following a formula, then generally my cloud will be very dense around a certain pattern. Otherwise it will start spreading. Yes?
So the more spread they are, the larger
the more diffuse.
The freedom they have.
The more diffuse, the less strongly correlated they are. So again, the two values here is strong and weak, and the two values here is positive and negative. Okay, so the correlation can be strong, as in this case, or weak, as in this case, where the whole cloud of dots is more diffuse in the area. And positive or negative, it has to do with whether it goes downwards with a negative slope or whether it goes upwards with a positive slope. Okay? Again, I decided to play a little bit of showing you different distributions and how they affect. Now, notice something. Considering that the income affects the weight right now, let us fix this. Take this as granted that causality goes from income to weight. How is the income distributed? By model. How is the weight distributed? By model. But notice, they are negatively correlated. So these numbers here, which are lower incomes, will be back to higher weights. And these are higher incomes, and they will be back to lower weights. The effect in this case that they have a negative correlation is that if, for example, income goes like this, and it's skewed, then weight will go like this. if income will be bimodal, and I will try to make it asymmetric to demonstrate this clearly, so bimodal. And I would expect the same thing to be reversed here. That's because when something happens to fall in this area, it will push if they are dependent. Again, we see that the two modes are forming two clusters. One cluster is because of this subpopulation with the low incomes and high weights. They're occupying this cluster. And the other cluster is this subpopulation with higher incomes and lower weights. Okay. Okay, finally, they are independent. I made them independent. In this case, the two distributions could be anything. Following the same example as before, I made income have two modes, but I made weight be skewed left.
Okay.
Flip it. Where would be the peak? So it would be skewed left. Okay. Now, we have the following functions in Excel. Well, actually, the functions I can cover next time, but I can show you one thing today because in the very limited time that we have. Right click on the data, add trend line. Make sure the entire data set is selected. So, right click on the data, add trend line, linear, display equation on chart, display R squared value on chart.
Up trend line.
Right click on the data, add trend line, linear, display equation on chart, display R squared value on chart. Okay, look. You see here a linear function of the type mx plus b. M is negative. This tells me how they are correlated, negative. Okay. The second number, R squared, we will examine it on Monday more clearly. The second number is very near 1. This number, you can expect it to be between 0 and 1. When it is near 1, it means I have strong correlation. Okay, if we do the same thing in the other two examples, right click, add trend line, display equation on chart, display R squared. Now, as you see, R squared is smaller. I still have a negative slope. This still demonstrates that I have a negative correlation between the two. R squared is not so close to 1 as it was before. And as you can guess now, when I do it for the third cloud, that is the least dependent of all, I'm going to get the smallest R squared of the three. And in our case now, R squared right now is even less. It's less than 0.5. Now all these numbers, this number, and one more very important number, will not only come from charts, they can also come from specifically formulas in Excel, but this I'm going to show you on Monday. Right, that's it. Yes?
Just one more question.
Yes.
Does the R squared have to do with the distribution and like?
No, No. The reason I talked to you about the two distributions was to show you how dependence basically duplicates the distribution. Dependence duplicates also the nature of the distribution. But what you really care is, from that trend, how close or how far the various data are. The distribution only has to do with whether you have clusters of data here or here, as I showed you before, but not whether they are strongly or not correlated.
But the lower the R is, the higher the variability.
The lower the R is, the more scattered the data will be, more diffuse the cloud. That's the way to put it. This cloud will be more diffuse.